Evening, everybody, to this second industry session. Today we have with us Cody Jones and Ryan Babbush from Google that will be talking about quantum computing science at Google. So I guess the first one will be Cody. So please, Cody.
Thank you. Good morning from California. Good evening to our hosts in Europe. I'm Cody Jones. I'm one of the research scientists at Google working in quantum computing. So for the first part of our talk, I will talk about some of the work and research towards quantum error correction. So I'll begin with just kind of a big picture of how we're thinking about quantum error correction right now at Google. So we've made some demonstrations with quantum computing in the past, and we're going to proceed to make a new quantum chip. So I've shown a picture here of a previous quantum chip. And then what we're thinking about doing is we want to run some experiments to implement surface code quantum error correction. So I've shown here some diagrams of a distance 3 and a distance 5 surface code in the rotated layout. And the idea here is that these are the two smallest versions of this code, and the distance 3 version will fail with 2 errors, and the distance 5 version will fail with 3 errors. So what we want to do is run an experiment where we implement a certain number of rounds of syndrome measurement, and we analyze the data to see if the failure probability is lower with the larger code. And so that is our way of saying that quantum error correction is working, that increasing the size of the code reduces the logical error rate. So we have this kind of high-level technology roadmap where, looking back to 2019, there was this beyond classical demonstration, and that's those are chips that we have today. And then looking forward, soon we want to demonstrate a logical qubit prototype. That's what I just described on the previous slide. That's around 100 chips. And then moving beyond that, we want to demonstrate that quantum error correction is working and that you can scale up. And there's a diagram here on the right-hand side of just what might that look like to have a large system. So the goal for the next several years is to show that quantum error correction works, starting first with a logical qubit prototype and then making a substantially larger surface code. But what I'm going to talk about in these slides are like, okay, well, what are we thinking about, in terms of implementing quantum error correction, proving that it works, and also alternative paths that are not necessarily the surface code. So the basic idea, this is probably familiar to everyone here, but we want to reach very low error rates by increasing the code size. So when you increase the size of the chip, the number of qubits, you can place larger surface codes. And so we describe the rate at which logical error is suppressed when you step up the size of the code with this parameter lambda. Lambda is simply a scalar number. And for example, I've shown a plot here, which is just like a semi-log plot showing logical error rate going down exponentially as a function of code distance. In this case, about a factor of 10, lambda being about a factor of 10. So we want a reasonably large lambda. Obviously, if lambda is close to 1, you don't get much error suppression factor. So what are some of the research areas that we have in quantum error correction at Google? I'll talk about these in the following slides, but a few things that we're very interested in. We're interested in real-time syndrome decoding. So I said we want to operate a quantum chip, and eventually we're going to need to be able to do this in real time in order to operate a quantum computer. Many of the published studies in quantum error correction, they demonstrate proof of principle syndrome decoding by solving a finite volume, but in a real system, it's a continuously running, you're continuously accumulating syndrome data. We're also interested in alternatives to the surface code. Perhaps the surface code looks great, but maybe there's something even better. But there's some challenges. The surface code is a front runner for quantum error correction for some good reasons. And then finally, what makes a convincing demonstration of quantum error correction? I'll talk at the end of this section, what are some of the open questions about this plan that we have? So first of all, if you're moving towards working quantum error correction, there's a simple but important change in the way you design your system. So where we are today is we have some input to describe an experiment. We generate signals that go into our device, and we measure the reflected signal that comes out, and that's why we determine the measurements in the quantum circuit. And then there's some post-processing, but there's no feedback. So in the right diagram, it's a very simple modification, but we're actually going to create a system where there is feedback. So in this green box, we need to do syndrome decoding, and this is going to, the results of syndrome decoding will be fed back into the experiment control because we need to react to that syndrome information. And I'll talk about that in another slide. But we need to be able to do this in about 3 to 5 years. And when I say in 3 to 5 years, I mean to have the capability of processing large surface codes in real time. So from an engineering perspective, what are some of the challenges with quantum error correction? Well, something that's probably pretty obvious is that redundancy is expensive. So for each encoded qubit, you might need something like 1,000 physical qubits, for example, at a distance 25 surface code. These parity measurements, they repeat about every microsecond. Now that's a value specific to our technology. Obviously it can vary a lot for other technologies, but it's highlighting for us what the challenge is. That we're going to have information coming in every microsecond, a new round of syndrome measurements. And so finally, QEC has stochastic branching behavior. So when I say branching behavior, I'm talking about the flow of the quantum computation. So some gates are deterministic, such as initialization and Clifford gates, but non-Clifford gates have branching behavior with 50-50 probability. And so when that branching happens, we need to actually have up-to-date syndrome information in order to determine which branch happened. So kind of summarizing in the lower right, in order to correct when an unwanted branch happens, we need up-to-date processing of the parity data. And this parity data is coming in continuously in real time. So we need to process it in real time with low latency. So I'll actually focus a little bit more on that to be specific about what we mean. A common branching example is if you're doing a T-gate with a magic state. So what happens is you use distillation to, well, you inject magic states into your surface code error correction, and then you use distillation to make them high fidelity encoded magic states. And finally, you can do a teleportation gate that consumes this magic state. The challenge here is that the teleportation process actually has a random outcome. And so if this measurement gives you 1, you actually have to apply a correction in the form of an encoded S-gate. So the challenge, however, is that you need to know what that measurement result is in order to do the S-gate. And knowing that measurement result requires up-to-date syndrome process syndrome information. So in the surface code, as you all know, syndrome measurements are faulty, so we are repeating them continuously. And we deal with this faulty syndrome by solving matching on a 3D graph. Of course, there are a few alternatives to matching, other syndrome processing algorithms for the surface code, but matching is perhaps the most common. And so every clock cycle, which for us is about a microsecond, a new 2D sheet of information appears on the graph. That's the measurements that we just made, which get converted into detection events, which is when a stabilizer parity flips. And so we're performing matching, but we need to be doing this on a continuously evolving graph, a graph that is growing in time. And that's because at some point we're going to do a measurement. I've drawn that in the diagram here as green is the measurement. And you could think of this as the 2 logical qubits from the previous slide, the left one being the magic state. There's a C0 gate that isn't shown here. But the point is, we need to have processed the syndrome information for the left qubit to get the measurement result to determine whether or not we apply a correction to the right qubit. So you have to do this in real time or your computation will stall. So this is one of our challenges is how do we do this in real time? It turns out to be computationally quite demanding. Another subject that's very interesting to us, we're looking at alternatives to the surface code. So some examples include color codes or LDPC codes that could offer different performance characteristics. So LDPC codes, they can have a lower ratio of physical qubits to logical qubits. This is by having a higher encoding rate. And color codes, they are appealing because they have transversal Clifford gates. They also may have more direct routes to implementing non-Clifford gates, perhaps reducing the resource cost there. And they potentially have a lower physical to logical qubit ratio, and that's just a property of the codes. They require perhaps half as many qubits or 2/3 as many qubits. But there are some challenges with these codes. One is that there needs to be, for our technology, there needs to be a way to map them to a 2D nearest neighbor connectivity. So I've drawn here an example. Let's imagine you need to mediate a gate between these two orange qubits labeled orange, and the dashed line is the gate between them. Well, in our technology, because we have connectivity on a square grid, you would need to mediate that interaction somehow. For example, maybe by doing some swap gates. That has some costs associated with it, both in terms of added error and scheduling problems. Another challenge with these alternatives to the surface code is that we need fast and accurate decoders for circuit level noise. So matching, emerged very early on as a very good decoder for the surface code, and I think that reaching similar levels of performance with other codes is still an open research problem. So finally, something that we think a lot about at Google is what makes a convincing quantum error correction demo. So like I said before, under assumptions about errors being local, we can forecast that logical error is suppressed by a factor of lambda each time the code distance increases by 2. But you can see there, we're making some assumptions. So in this diagram here, I've added on top of it, let's suppose that, we make the two smallest surface codes, and because it's the near term, we're just a little bit below threshold. Lambda is a little bit greater than 1. And then, well, what can you forecast from that? There's a question mark. So I think something we're very interested in is like, what experiments could we do that would give confidence that the logical error can be suppressed, say by a factor of 10, or at least something substantially larger than 1? These are some open questions, and we're actually, we're pursuing these ourselves, but we're also interested in working with the academic community to get more comprehensive theory so we can make fewer assumptions. So with that, I'd like to hand it over to Ryan, and he's going to talk about some of the quantum algorithms work that we have at Google.
Great, thank you, Cody. All right, I'm just going to assume that people can hear me and see my slides now. So the intention of this talk today was really to give a perspective on the type of work that we tend to focus on that's more of a computer science variety at Google, since QIP is a computer science conference. Cody talked about our work on error correction, which is a big part of that. I'm going to tell you a bit about our work on algorithms. So to start with, I just want to reemphasize that our hardware team is essentially dedicated to 2 goals. So one goal is to try to deliver the world's best quantum computing service. And another goal is to build an error-corrected quantum computer, which Cody was just talking about. So the theme of my talk today, to some extent, is that one thing that we work on, but something we also need the help of the community with, is we need help figuring out what we're going to do with both of these things. So I'm going to talk about sort of both sides of this, and I'm going to start by saying a few things about our quantum computing service. So the devices that Google used to demonstrate quantum supremacy in 2019 are now available via cloud access. There's a relatively small number of academics who are using it already, accessing it externally in order to implement their own experiments. And we've also published a number of papers just in the last year, which have mostly been from our own team, but at least one now from an external party that is using these chips through the cloud. So for example, we had a quantum chemistry experiment that was sort of the largest NIST chemistry experiment that is shown here, was on the cover of Science. We had a paper on QAOA, which actually came out today in Nature Physics. And then more recently, we had a simulation of the Hubbard model, which was involved very large circuits. It had actually over 5,000 gates and still got reasonable data out. And there were a couple other papers on calibration methods, on scrambling and out of time order correlators, and also one demonstrating a machine learning experiment. So our quantum computing service, it works sort of like you might expect, like most of them do. The point is that you can, send jobs through the internet, and they communicate with our quantum computers, and they run your circuits and you get the data back. And like, the other companies, we also provide our own set of open source tools. We have Circ, which is our API for programming quantum computers. We have Open Fermion, which is a special purpose library for quantum simulation. TensorFlow Quantum is a special purpose library for quantum machine learning. And we have some libraries for simulators and for demos as well. So here's a quick data sheet I'll show you on one of the processors that we have in the fridge today. It's one of our Sycamore processors. Currently, when this data sheet was taken, there were 51 qubits up and running. The sort of median 2-qubit error rate was about 1%. With the single qubit error rates about 10 times less than that. So we're pretty proud of how these chips are performing, but there's still some work on our end in order to sort of stabilize their performance through the cloud and offer calibration tools that really allow users to get the best performance out of them. Okay, so great, we're offering some chips through the cloud. What are we actually going to do with these? So I think to some extent our perspective is that we're really focused on getting to quantum error correction, but we're going to have these NIST devices sort of by definition until we get to quantum error correction. So we might as well try to use them. Now, as the QIP community knows well, a lot of NIST is pretty messy. I mean, a lot of these algorithms are heuristics that have a few performance guarantees, and for a number of the proposed NIST applications as they're described today, I'd say that a number of them have some rather dubious prospects. And I think there's really a relatively small number of papers that seriously try to estimate the resources required to exceed classical algorithms for a NIST application. That's generally very hard to do. Of course, some of the work that does try to do this is not really focusing on an application, but is just trying to focus on what is sort of the simple experiments you could run that are classically intractable, and developing better methods of doing the classical simulations, and then estimating what would be required for the quantum computer. And this was sort of the basis for our quantum supremacy experiment in 2019. But this by itself doesn't, well, it sort of has an application. There's this application about using it to generate certifiable random numbers, which is an interesting application, but that's probably not going to pay the bills for this whole endeavor. So we're hoping for something more than that. Personally, I think it's likely that there are some sort of physics applications that would be possible in NISC in quantum simulation. But I think there's sort of a spectrum of different applications in quantum simulation. And on one side of the spectrum, you have things that are sort of looking already a lot like our quantum supremacy experiment. So, you could say that random quantum circuits are, scrambling unitaries, and scrambling is of interest to understand how black holes work or something like this. And so therefore, if you measure OTOX and scrambling unitaries, you're doing some sort of physics experiment that a condensed matter physicist might care about. And that sort of thing, I think we're definitely able to do. You might sort of think a little bit further down the spectrum and say, well, the devices we have, they're essentially spin Hamiltonians on a lattice. So maybe we can do some classically intractable simulations of the time dynamics of such models. And, maybe such models describe magnetism or spin glasses or something like this. And, I think that's reasonable as well. If you go even further on the spectrum, you could think about, instead of having spins, having fermions, and having, not just nearest neighbor connectivity, but higher and higher connectivity, and eventually you'd have something like this, a realistic description of a molecule. And, I think there really is, of course, a big question of whether we're going to be able to get to such sort of, let's say, industrially relevant applications of quantum simulation, in the classically intractable regime in the NISC era. So we're trying, we'll see how far we get there. So you might ask, why provide a quantum computing service at all? And it's a non-trivial question because the reality is that serving access to these devices through a cloud, it does divert resources, some resources from our quantum error correction effort. There's, a lot of the hardware team needs to focus on stabilizing access to these things. But the reality is, and I think the answer is that, and I'm not just talking about Google here, but I'm talking about, the whole sort of large quantum computing industry, is just, it's not going to survive long term without compelling applications of quantum computers. And there is a real risk that it's going to take a very long time to get to quantum error correction. So I think we'd all feel a lot better if we could find something in the NISC era. And towards that objective, part of our hope is that cloud access to our chips will provide a tool for developing NISC applications, and or perhaps will also provide incentive for people to think about that. And so, if you have an exciting idea that you think might be appropriate to run on our chips, that you really think could do something interesting, please get in touch with us. We'd love to hear about it. And I'd also like to emphasize that I think when we're sort of evaluating experiments, we tend to think that the best experiments are those that really teach us something that we couldn't learn without actually running the experiment. And a lot of these sort of small scale algorithm demonstrations, it's debatable whether you're really learning something about the algorithm by using the devices, but even small experiments can teach us about, say, the properties of noise and how you might mitigate it. And that's sort of a critical topic for NISC. I think that if we're ever going to get NISC to work, we need ways of combating the errors that we face in practice. And so as a result, one thing that our team's been focusing a lot on is developing a sort of error mitigation technique. So just in the last year, essentially, I'm listing some papers here that are about different methods of error mitigation that our team has developed. And the blue ones here are theory papers, and the yellow ones here are demonstrating some of these ideas in experiments. Okay, so I've talked a good bit about NISC so far, but again, as Cody was sort of telling you, our plan of record is to build a surface code quantum computer. And we have a specific roadmap for building one with 1 million physical qubits. And it's going to be sort of a long road. We're going to have these NIST devices along the way. But during that time, we also have the opportunity to try to figure out what are we actually going to do with 1 million physical qubits, because, quite honestly, we have some ideas, but I don't think that we have really found the killer application yet. And I want to use this opportunity to just give sort of a technical opinion for a couple slides here, which is that one thing I think that we should not be really focusing on, at least for realizing on such a device, is algorithms that give only a quadratic speedup. I think that this point is appreciated by some in the community who study algorithms with an eye towards their fault-tolerant realization, but it's maybe underappreciated in the quantum community at large. So, I think most people know that in some sense, there are sort of massive constant factor slowdowns that are associated with quantum error correction. So to give some sense of this, here I've shown what's required to implement a classical NAND gate in CMOS. And if you want to think about it, space-time volume, you could say that it's less than something like 10 to the minus 9 transistor seconds. And of course, transistors we can make very small in space. Now, if you want to think about sort of the quantum equivalent of that, sort of a quantum NAND gate, I'm going to say a Toffoli is kind of like a quantum NAND gate. I mean, they're not exactly the same, but if the target qubit is in 0, then a Toffoli is like a reversible or is like a NAND gate. So, there's different ways that you could realize these things within the surface code, but using some of the best constructions that Google's managed to come up with in a cost model that's appropriate for our superconducting devices, it's looking like that a Toffoli gate would require around more than 10 qubit seconds in order to implement. And so there's essentially a 10 order of magnitude gap here between the space-time volume required to do, a primitive operation in CMOS versus on a quantum computer. So as you know, many proposed applications of quantum computers, especially those that are based on amplitude amplification, like Monte Carlo or search, optimization, promise only quadratic speedup. So that's really what people are hoping for. So if we imagine that we have a classical algorithm that's scaling as some constant c times n, we have a quantum algorithm that's scaling as some different constant q times the square root of n. So, we have a quadratic speedup here, but there's different constants, C and Q. Then if Q is much, much, much larger than C, we still need a very, very large N, which would probably correspond to running the computation for a very long time or needing a very large quantum computer in order for the scaling advantage of the quadratic speedup to overcome this huge difference in the constant factors and actually win. Now, in contrast, if you have an algorithm that gives you an exponential speedup, it's unfortunate that we have this large constant factor difference, but usually the sort of exponential scaling will quickly close the gap between these constants so that you can get a quantum advantage. And so, I think most of us sort of got into quantum computing because, exponential speedups are very exciting and quantum computers do promise that. So maybe we're not so worried about those, but for quadratic speedups, there sort of might be a problem here. And I also want to emphasize that many applications where a quantum computer is giving a quadratic speedup, not all of them, but many of them are classically very easy to parallelize. Like that would be the case for a lot of Monte Carlo or search or something like this. So I want to say just a little bit more on this particular point. And I'm going to use a little bit of data from this paper I'm listing here, which is a paper that actually there's a QIP talk on from Yuval Sanders tomorrow. But this is a work that Google did on basically compiling various heuristics for quantum optimization in order to error correcting codes, and basically asking the question of what is sort of the constant factor required to realize these primitives. And we were then able to basically ask the question, based on the difference between how sort of long classical algorithms would take and what these constant factors and the error-corrected realizations were, we could essentially ask, how hard must the problem have been, or how long must the quantum/classical computers run for in order for the scaling advantage of the quadratic speedup to overcome these large constant factors, and you could actually see a quantum advantage. And for example, one of the algorithms that was sort of looking most favorable to the quantum computers in our analysis was the quantum accelerated simulated annealing algorithm, where this is basically a quantization of the classical Markov chain for simulated annealing. And in one of the problems we focused on where the numbers came out most favorable for the quantum computer, what we found was if we were using our 1 million physical qubit quantum computer and sort of comparing to classical computers doing simulated annealing on this problem, if you're comparing to one core classically, it would take about 320 days. If you're able to parallelize things classically, this crossover point was even much more discouraging. We also had another paper out, which was basically making an argument sort of against quadratic speedups on these error-corrected processors in a more general sense. And it's more of a perspective piece. It's a bit hand-wavy, but we basically argue for sort of a lower bound on the best sort of gap in performance between the constant factors in quantum and classical algorithms that you could hope to have for really any algorithm that would give you a quadratic speedup. And here, the numbers turn out to be a little bit better for this very optimistic analysis. Maybe 2.4 hours to see a crossover if you're comparing to one classical core. But if you're able to parallelize well classically, then again, these numbers become extremely discouraging. But we also did a similar analysis for other sorts of speedups and found that for higher order speedups, this crossover point doesn't look nearly as bad, which was actually a little bit surprising to me. But I think it's encouraging. There are some quantum algorithms that give cubic or quartic speedups, and maybe those would be viable on a smaller error-corrected quantum computer. So I think that's kind of an interesting point. So anyways, also, we sort of did this analysis under, assumptions are kind of specific to the way we're thinking about realizing error correction, but the essential conclusion for quadratic speedups essentially persists, even if we were to very dramatically increase the rate at which we could implement error correction. So to some extent, I think this is fairly fundamental. Okay, so I've sort of made the point that maybe quadratic speedups, which are unfortunately the class of, the algorithms giving quadratic speedups, they tend to have very broad applicability. But there are, of course, other areas where we could, hope to find good applications of quantum computers. One of the first things that comes to mind for many people is Shor's algorithm. I think, many of us wouldn't be here if it weren't for Peter Shor. Certainly there's an exponential speed up there. And there's a paper I'm listing here, which was some Google work on sort of pricing out the quantum resources that would be required to break 2000-bit RSA encryption. We'd need about 8 hours, about 20 million physical qubits. So maybe not a million physical qubits, but it's not an astronomically large device. But the reality is that's, as far as we know, that's not really the application we're looking for. Google certainly doesn't want to be in the business of helping people break encryption. Once we get to that point, people maybe wouldn't be using that encryption. A lot of our other work these days is now thinking about some other applications. One that I think is especially interesting that we're doing some work on currently is in quantum linear algebra. So algorithms like the HHL algorithm, they, of course, in principle, they give an exponential speed up for solving linear systems of equations. But in practice, there are sort of a number of tricky conditions that have to be met to realize that advantage, which many of you are probably familiar with. But you have to have special structure in the linear system of equations such that you can kind of query the sparsity of these matrices or simulate them on the fly in some efficient fashion. You can get some bad scaling that sort of creeps in from the way these quantum algorithms scale with the condition number in some contexts. You have to be able to prepare the state B efficiently. You have to be able to sample from the solution vector that you're preparing. So there are definitely some challenges there. I think that a number of people are of the opinion that differential equations, linear differential equations, which you can solve by sort of implicitly updating them with these linear algebra algorithms. Those sort of seem promising because often differential equations, they have the sort of structure in them that you need in order to be able to implement HHL efficiently. But of course, there's some challenges here. For example, you need to find differential equations which are sort of high dimensional, and you're probably looking for ones that can't be solved with Monte Carlo, because if it can be solved with Monte Carlo, that often is giving an approach that also doesn't explicitly scale with the dimension. You might be able to get a quadratic speed up over Monte Carlo, but that's not really what we're looking for. So I think this is a promising area, but I think it's yet to be seen, is there sort of like a killer sort of industrially or scientifically important application of these linear algebra algorithms where all the conditions are really met. I think that's something we're interested in understanding better. Machine learning is always a trendy topic, of course. And there's a lot of work on machine learning that is using sort of QRAM, where the speedups maybe don't persist if you leave that oracular model, or there are many quantum machine learning algorithms that are giving a quadratic speedup. But there are some algorithms that are looking more promising. And I guess I would say that more generally, we do know that clearly quantum computers can help us sample from probability distributions that would be classically intractable to sample from. For example, just you could say that we're doing this in the quantum supremacy experiment. And, so to some extent, then a lot of machine learning, it's really just sort of about learning probability distribution. So I think a critical question is, sort of what properties in data sets might lead to a quantum advantage in modeling them? What properties of data really require the sort of, unique quantum capabilities in order to model? And this is, of course, still an open problem, and it's a difficult problem, but it's a topic Google's been thinking a lot about. Robert Huang will present some work tomorrow as well, which is sort of a merger of a paper that he worked on with our team and some work that he did with Preskill's group in machine learning. So you should definitely check that talk out. Okay, well, what about everyone's favorite topic, certainly my favorite topic, which is quantum simulation. Fortunately, we do know that there are many exponential speedups available in simulating physical systems, which is good. I think that there's still a question, though, of are we going to be able to have a really large and robust industry in quantum computing in the long term around quantum simulation? And people have worked out a number of examples of specific problems where quantum computing could help. One that you might be getting sick of seeing is this fertilizer production problem. It takes 2% of the world's energy to make fertilizers. We currently do, but there's some enzyme that lives in the soil that does this with essentially no additional energy. And there's this sort of magic active side of this enzyme called FOMOCO, where it basically is the catalytic site where it binds nitrogen and fixes nitrogen and makes fertilizer. And the electronic structure, the quantum chemistry of this is very complicated. And it's been pointed out, if we had a quantum computer, we could just we could maybe figure out how that mechanism works. And so there's been a number of papers competing on how best to do that. And a paper that was some Google work that was presented as one of the short plenaries on the first day of this conference, Dominic Berry presented it, was giving the sort of lowest scaling algorithm and best compilation so far for solving problems like this. So this is definitely an application that we care about. And we concluded that about 4 million physical qubits and about 4 days of runtime would be required, if we have about 10 to the minus 3 error rates. So, I think that's starting to look pretty encouraging. And there's a lot of other applications in chemistry. And, personally, I'm very optimistic that the ability to make calculations like this will really usher in sort of, a new paradigm of being able to understand the chemical world, which could really translate into the development of technologies. But, it should be said that, for example, just understanding the mechanism of how FOMOCO binds nitrogen, it doesn't mean that we're going to just be able to instantly develop a new industrially scalable catalyst that will significantly reduce the cost of making fertilizer. There still needs to be a lot of, clever sort of chemists thinking about, okay, that's how the mechanism works. Well, what if we made a catalyst that looked like this? Would that have the same mechanism? And you could use the quantum computer as a tool in this endeavor. But I think once you really think about quantum simulation as a tool, kind of like a spectrometer or something like this, it will help us understand things, but it's not sort of immediately going to translate into value in the same way that, for example, some applications in optimization or in, say, derivatives pricing or something like that might translate into value if those applications could actually give a viable speed up on a small error corrected device. And it's not clear they could either. So maybe to just summarize an outlook on error corrected applications and let this be sort of a call to action for our community to, really try to help think more concretely about what we're going to do with error corrected devices. Again, I want to reiterate that we probably are going to need to do better than the broadly applicable quadratic speedup algorithms. And, I think that there's reasons to doubt that, a modest error corrected quantum computer will actually help with things like, options pricing based on Monte Carlo, because it's just giving a quadratic speedup. Of course, machine learning and optimization, they have very, very broad appeal. And so everyone's very excited about them. But I think that the best hope for having a very substantial, better than quadratic speedup in those domains is really to find instances that have very specific structure, and thus, it might not turn out to be so broadly applicable once you focus on that. These quantum algorithms for linear systems, they can be studied formally. They give an exponential speedup in a sense, but we still need to find a problem that's a perfect fit for them. And of course, there are industrial applications of quantum simulation, and I think that is very promising, but it's still important to refine how those simulations are going to help us advance technologies. But surely, I think there must be other applications as well, and we really look to the academic community for help in figuring those things out. And so on that point, I just want to highlight that Google gives millions of dollars a year to academics to assist with our research. So there's a number of different ways that we do this. For example, we tend to give fairly targeted sort of assistance to help with specific projects that sort of advance the kind of agenda that I was just telling you about. But for example, there are direct grants to help fund your team to collaborate with Google. We do sponsored research agreements, which are sort of varied, but they can be a combination of sort of grant funding and also personal compensation for PIs who are working with Google. We have visiting academic positions, which could be sort of full-time. Like if you're a professor, you can come do a sabbatical with us for a year, or we have ones that are sort of just 1 day a week, and you could really be part of our team, but working just 20% time while retaining your university position. We have PhD fellowships and internships for excellent students. And of course, if you have a cool idea for what to do with our chips, we have this cloud service now, and we can give people time on our chips. The final slide here, I want to emphasize that our team is hiring and we're growing a lot. So we've recently sort of landed the concept of this longer term, 10-year roadmap for building an error-corrected quantum computer with the executives at Google. And, as part of ramping up our ability to, execute that roadmap, our team is going to be growing by 150% over just the next 3 years. So we're hiring a lot of positions in sort of all areas of the team. And we're looking for research scientists, hardware engineers, software engineers, theorists, interns. We have some active roles posted on our team website, but that's not really representative of all the areas that we're hiring in. So you can also just sort of email us and send our team your resume and get in touch with us. So with that, I want to thank you all for your time and wish you a great QIP. Thank you.
Thanks a lot, Ryan and Cody, for these very nice talks and for all the insights that you provided us with. So I guess we have now some minutes for some questions. Some of them are coming here in the Slack channel. So for example, Minyu Kang is asking, what is your prospect about quantum machine learning finding a better solution instead of finding a solution with a speedup?
Yeah, well, I hear this question a lot, and I could be mistaken, but to some extent, my perspective is that you can always phrase any problem as being in terms of a speed up. So when you say like a better solution, for example, maybe you mean a more precise solution, and so then maybe you really need to say, be careful and specify the problem in terms of epsilon or something like this, and say that the problem is actually to, produce a solution that's accurate to within epsilon, and then you have to worry about the scaling with epsilon. Or maybe you mean that the solution is sort of qualitatively different in some way, but you should be able to quantify, I think, what that means, how it's different, and say then that the problem, in fact, is to produce, a solution that doesn't have these characteristics or something like that. And so I think that if you are really careful about how you redefine the problem, that often it can be phrased in terms of a speed up. But I'm open to counterexamples on that, though.
I see. Thanks, Ryan, for your answer. Yeah, I guess it's necessary not to define what better means in this case. So there are no more questions so far. I just wanted to ask you personally, I'm curious. The actual platform that Google is using to implement qubits is our superconducting circuits. Is Google exploring any other kind of platform?
I think that we're paying close attention to progress in a number of different platforms. And, we don't see ourselves intrinsically as like a superconducting qubit quantum group. If we felt that there was another platform which was, which we thought had better prospects for scaling to build a fault-tolerant quantum computer, we would very seriously look into pivoting to that. And we do have discussions about that somewhat regularly. But no, at the moment, we're fairly convinced that the best way forward for us is superconducting qubits. And that is the technology that our team is dedicated to working on.
I see. So I guess I will take the last question so far. It's asked by Alexander Müller Hermes, and he's asking, what is the dominant noise affecting your devices?
I could field that one. So probably if you had to pin it down to one single thing, I would say that it is T1, energy relaxation, is the dominant noise mechanism. So it's an ever-present sort of passive noise source. But it can show up in a lot of different ways. Like T1 obviously affects qubits while they're idle, but it affects them during gates, and it can even affect the fidelity of your measurement. So If you're looking for like a single physical process, that's what I would pick.
Okay, I guess I had some problem with the internet connection. Have you finished answering, Cody? I'm sorry.
Oh, yeah. So I hope that I came through clearly because I wouldn't know. But yeah, I said that I think T1 is the dominant noise process.
Okay, thanks a lot. Yeah, I just had the image frozen. Okay, so thanks a lot again to both of you. Again, remind the audience that if they want to interact with you personally, they can go to the round at the end of the session. So right now, let's welcome our next speaker, Sarah Sheldon from IBM, that is going to talk about demonstrating the capabilities of state-of-the-art quantum systems. So I guess, Sarah,